We often assume that bigger means better, especially when it comes to brains, but is a large brain really a sign of high intelligence or just a more expensive organ to maintain? Today on Your Body's Clues, we're cracking open the skull-sized mystery behind brain size, IQ, neuron count, and why evolution didn't give gorillas a PhD. Get ready for a surprising, science-backed journey into the true cost of thinking. Intelligence has always been elusive, hard to measure. Harder to define. It's not just about solving math problems or memorizing facts. It includes creativity, adaptability, emotional insight, and the ability to learn from failure. And yet, one idea continues to echo through pop culture and casual conversation. Bigger brains must mean smarter people. At first glance, it seems to make sense. After all, more brain means more neurons, right? More wiring, more capacity. And to a certain degree, research has shown a moderate correlation between brain size and performance on standardized IQ tests. Statistically speaking, individuals with slightly larger brains do tend to perform a bit better on average, but here's the catch: that correlation is far from absolute. It's modest at best and easily overshadowed by dozens of other factors. Because intelligence isn't stored in a single place, it isn't just about how much brain tissue you have, but how it's used, how well it's connected, how efficiently it functions, and how your experiences, education, health, and even sleep shape your cognitive ability. A larger brain may offer potential, but potential alone doesn't guarantee brilliance. Some animals, like whales and elephants, have far larger brains than humans, and yet human intelligence outpaces them by far, due to factors like brain-to-body ratio, cortical folding, and specialized regions. So the real question isn't just how big your brain is, it's how effectively it's wired, how adaptable it is, and how you use it. Because when it comes to intelligence, more doesn't always mean better, and a premium mind doesn't come from brain volume alone, but from the way your biology, experiences, and behavior come together in a kind of cognitive symphony. At birth, humans are strikingly fragile compared to many other animals. We arrive in the world with remarkably underdeveloped brains, unable to walk, feed ourselves, or even lift our heads. We depend entirely on others for survival, for warmth, for nourishment, for protection from the world. In evolutionary terms, this seems like a strange design flaw. After all, wouldn't it make more sense if survival and reproduction are the goals, to be born with a more complete brain, more ready, more functional, capable of crawling away from danger or even feeding ourselves? And yet, evolution chose a different path for humans. Why? Because the trade-off lies in our brain's potential, not its immediate power. If the human brain were to fully develop inside the womb, it would require a skull too large for the birth canal. Childbirth, already a precarious process, would become impossible, so nature made a compromise: let the baby be born early before the brain is finished, and allow development to continue outside the womb, where experience, environment, and social interaction would shape the brain in ways biology alone could not. In other words, we are born unfinished on purpose. This strategy gives us something no other species quite possesses: an extraordinary level of neuroplasticity, the ability to mold and reshape the brain after birth. It makes us learning machines, wired for bonding, for curiosity, for adaptation. Yes, it costs us a longer, more vulnerable childhood. Yes, it demands more from parents and caregivers, but the reward? A brain that's not only big, but built for possibility. And in the long arc of human evolution, that vulnerability became our superpower. To understand why human birth is so precarious, why our babies are born so helpless, and why labor is so uniquely difficult among mammals, we must explore what scientists call the obstetrical dilemma. It's one of evolution's great biological negotiations. As humans evolved to walk upright, our bodies underwent dramatic changes. Standing tall on two legs required a restructured pelvis, narrower, tilted, and better aligned to support bipedal motion. A slimmer pelvis made walking more efficient. But it came at a cost, because at the same time, our brains were growing rapidly, generation after generation. The human cranium expanded to support more neurons, more cortex, more complexity, but the birth canal shaped by the pelvic bone didn't expand with it, and so nature found itself caught between two opposing forces. A smaller pelvis was essential for balance, mobility, and upright posture. A larger skull was necessary for the growing intelligence of our species. The result? A compromise, not a perfect design, but a delicate middle ground. Human infants now develop inside the womb just long enough for basic survival, but not long enough to finish brain development any longer, and the head might not fit through. The birth canal, this is why human childbirth is so uniquely dangerous and painful, why we require help, support, and medical attention even in modern times, and why, unlike other animals that walk shortly after birth, our newborns arrive unfinished, fragile, and dependent, but this biological trade-off brought something profound. It gave us the ability to walk upright and to think complex thoughts. It demanded that we evolve not only physically, but socially, forming communities, offering care, passing knowledge down. In that sense, the obstetrical dilemma didn't just shape the body, it helped shape civilization, because in order to survive, we had to work together. The obstetrical dilemma doesn't just explain the difficulty of human birth, it also reveals the hidden logic behind why our babies are born so unfinished. Human infants arrive into the world far less developed than most other mammals. They can't walk, speak, or regulate their own bodies, but this vulnerability isn't a flaw. It's part of a carefully balanced biological compromise, because in order to pass through the narrow birth canal, the human brain must continue growing outside the womb. This is why, in the first year of life alone, a baby's brain triples in size, a period of growth so intense it's rarely matched again, and the skull, that delicate shield for the brain, comes not fully fused, but in pieces, soft plates separated by sutures and fontanelles, what we call the soft spots on a newborn's head. These aren't design flaws, they are flexible seams, an evolutionary adaptation that allows the skull to compress and fold, squeezing safely through the narrow birth canal. It's a brilliant workaround, but it comes at a price. For months after birth, the baby's brain remains exposed beneath soft tissue, with no solid bone to protect it. A fall, a blow, even rough handling can be dangerous. The very thing that allows us to be born at all also makes us fragile beyond compare, but this fragility sets the stage for something powerful. It allows the brain to keep growing not just in size, but in flexibility, adaptability, and responsiveness to experience. It allows the world to become the womb, where language is learned, where love shapes neurons, where life continues. The work biology only began. For years, the prevailing view has been that human babies are born prematurely early, fragile, underdeveloped, a direct result of evolutionary trade-offs like the obstetrical dilemma, but new research is beginning to challenge that idea when we compare ourselves not to adult animals, but to our closest relatives. Primates like chimpanzees, bonobos, and gorillas. A different picture emerges. Their infants, too, are born helpless. They can't walk on their own. They rely on caregivers for food, warmth, safety, and emotional regulation, and they stay closely attached to their mothers, sometimes for years. In this light, human newborns are not uniquely premature. They are simply part of a broader pattern found in the primate lineage, a long, slow developmental arc. What sets humans apart, then, isn't how early we are born, but how far we go after birth. Our dependency phase is longer, yes, but so is our brain's period of plasticity, so is our window for learning, for language, for social bonding, for creativity. The prolonged vulnerability of a human baby isn't a delay, it's an extension of possibility, because instead of finishing development in the safety of a womb, human brains continue to form within relationships shaped by interaction, by emotion, by experience. So perhaps our babies aren't born too soon, they're born right on time into a world that will become their second womb, filled not with amniotic fluid, but with voice, touch, and meaning. At first glance, the solution seems obvious. If the problem is that a baby's head is too large for the birth canal, why wouldn't evolution simply broaden the female pelvis? Wouldn't that solve everything? But here's the surprising truth. There's no strong evidence that a slightly wider pelvis would hinder walking, running, or any of the complex functions the human pelvis supports. Modern studies have shown that a broader pelvis doesn't significantly reduce locomotor efficiency. In fact, women already have a wider pelvic inlet than men, and they walk just fine. So, if brain size was the only evolutionary pressure, wouldn't natural selection have simply gifted mothers with roomier hips? It turns out the story is far more complex than a matter of skeletal dimensions, because brain development isn't just about size, it's about timing, energy, and adaptability. A bigger brain means more neurons, but also a higher demand For nutrients, especially during growth, it places enormous strain on the mother's metabolism during pregnancy, and on the infant's ability to survive once born. There are biological trade-offs at every stage. A longer gestation could increase the risk of complications. A larger newborn head might not only strain childbirth, it could strain survival. Post-birth, a wider pelvis might slightly ease delivery, but would do nothing to address the metabolic, neurological, and developmental demands that come with a bigger brain. In other words, evolution isn't a straight line, it's a balancing act between dozens of competing pressures: the shape of the pelvis, the timing of birth, the growth of the brain. None of it evolved in isolation, and so, the reason human infants are born when they are is not because evolution failed to widen the hips, it's because evolution found a rhythm, a delicate choreography of growth, energy, and survival that allowed our species not just to walk upright, but to think, learn, and become human. So if birth timing isn't solely determined by the shape of the pelvis, what is it that sets the clock? Emerging research suggests a powerful and often overlooked answer: energy. Rather than being dictated by bone structure or walking efficiency, human gestation may be limited by the simple, biological reality that a mother can only provide so much fuel. Throughout pregnancy, a woman's body performs a remarkable balancing act. She must nourish not just herself, but an ever-growing, rapidly developing child, and by the time she approaches 40 weeks, her metabolic systems are working near maximum capacity. At this point, her body reaches an energetic tipping point, the caloric demand of sustaining both her own tissues and the baby's growth becomes unsustainable. Put simply, she's out of fuel. The placenta, the gateway of nourishment, can only transfer so much, and even if the mother eats more, there's a ceiling to how much her body can digest, absorb, and convert into usable energy. So birth isn't just a matter of physical space, it's a matter of metabolic exhaustion. The baby must be born, not because the mother's hips say so, but because her biology is waving a white flag. If gestation were to continue beyond this point, both mother and child could face serious risks: nutrient depletion, compromised immune systems, stalled fetal development, even death. In this light, the timing of human birth is not a flaw, but a remarkably precise calculation of biological economics. Nature doesn't aim for perfection, it aims for what works, for what's just sustainable enough. And so, at the edge of maternal endurance, the body makes its call. The baby is born still unfinished, still fragile, but just in time to survive and to continue growing in the arms of others, because after birth, the mother's energy is no longer the only resource, the outside world food, touch, care, love becomes part of the development equation, and from that point on, it takes a village not just to raise a child, but to finish the work evolution began. If we follow the simple logic that a bigger brain equals greater intelligence, then we'd have to surrender our crown as the smartest species on Earth, because by sheer volume, we lose. Whales have the largest brains of any living animal, elephants come close behind, and both leave the human brain in the dust when it comes to raw size. So does that make them smarter than us? Most would hesitate to say yes, because intelligence, as it turns out, isn't just about mass. It's about how that mass is used. It's about efficiency, complexity, and the wiring between neurons, not simply the number of them. That's why researchers often use another metric, the brain-to-body ratio or encephalization quotient. This helps level the playing field between a mouse and a mammoth on this scale. Humans seem to fare better, but not by as much as you'd think. Our brain makes up about 140th of our body weight, the same as a mouse, not exactly the prestige statistic we might have hoped for. So what gives? The truth is, both total size and relative size offer incomplete pictures. A whale's brain may be huge, but much of it is devoted to managing an enormous body, coordinating movement, regulating temperature, navigating oceans. In contrast, human brains are highly specialized with disproportionate space given to abstract thinking, language, memory, social nuance, and planning. We also have something no other species seems to possess at the same level: a vast, intricately connected prefrontal cortex, which helps us imagine, reflect, and make complex moral decisions. So while brain size tells us something, it doesn't tell us everything. If intelligence were a luxury item, it wouldn't come with a simple price tag like bigger is better. Instead, it would depend on how much you get out of every ounce on cognitive ROI, return on intelligence, and in that category, humans aren't just efficient, we're extravagant, we use our brains to study the stars, write poetry, build cities, invent myths, and ask impossible questions like this one. So maybe the better question isn't, how big is your brain? But what are you doing with it? If raw brain size doesn't tell the whole story, then what does? Neuroscientists have proposed a more nuanced metric, the encephalization quotient, or EQ. This number compares an animal's actual brain size to the brain size we would expect for a creature of its body size. Because here's the thing, bigger animals naturally need bigger brains, not for thinking, but for basic maintenance, coordinating muscles, regulating internal organs, navigating physical space. These tasks require more neural machinery the larger the body gets, so the EQ tries to level the playing field. It asks, given your size, is your brain larger or smaller than expected? And in that arena, humans saw, we don't just have a big brain, we have a brain that's far larger than it needs to be based on body size alone. Let's put it into perspective. A mouse, for example, has a high brain-to-body ratio, but a low EQ. Its small body doesn't need much brain power, and most of its brain is devoted to simple functions, breathing, eating, survival. Not a lot of room left for abstract thought. Elephants and whales have massive brains, but their EQs are lower than ours. Much of that neural tissue is used to operate a massive, complex body. Dolphins? They come closer. Their EQ is impressive, one of the highest in the animal kingdom, but even dolphins don't quite match the human overachievement. Our encephalization quotient doesn't just put us at the top. It puts us well above the curve, the neural equivalent of a luxury item with performance far beyond standard specs. This excess capacity may explain our unique abilities: language, art, science, humor, self-reflection, the ability to imagine futures, question our past, and wonder about the meaning of it all. It also raises a profound question: why did evolution gift us with a brain that does more than we need to survive? Because we could still hunt, gather, reproduce, and avoid predators with far less grey matter. The answer may lie in how we've evolved not just as individuals, but as a social species relying on cooperation, communication, and culture. Our big brains may be the result of needing to understand each other, not just the world. So yes, numbers matter, and in this case, the encephalization quotient offers a compelling glimpse into why we think the way we do. Not because we're the largest, not because we're the strongest, but because, pound for pound, our brains are doing something extraordinary. For over a century, scientists and psychologists have chased a tantalizing idea that there exists a single, measurable essence behind all intellectual ability, a kind of general intelligence, often referred to as G. It's the notion that beneath all our varied talents, logic, memory, problem solving, creativity, there might be one unifying force. Something stable and quantifiable that determines how intelligently we think across domains. If such a force exists, the implications are enormous. Could we measure it reliably? Could we increase it? Could we design education, environments, or even technologies that help it grow? These aren't just theoretical questions, they're billion-dollar questions fueling an entire industry of IQ testing, cognitive training apps, brain-enhancing supplements, and educational reform, and yet, despite decades of research, the answers remain elusive. We do know this: people who perform well on one type of mental task often perform well on others. This pattern suggests that something general might be at work beneath the surface, a shared cognitive engine powering everything from math to memory to verbal reasoning. But we also know that intelligence is far from simple. It's influenced by genes, environment, nutrition, stress, education, social context, and even sleep. It can be shaped, supported, stifled, or stretched, but not easily defined. So when we talk about general intelligence, we're not referring to a single muscle or organ, but to a mysterious network, a dynamic interplay of brain systems that work together in complex, often unpredictable ways. And here's the most humbling part: even if we could measure it perfectly, even if we could enhance it at will, that still wouldn't tell us what it means to be wise or curious or kind, because intelligence, however we define it, is only one part of what makes us human. For over a century, psychologists have been chasing a single, elegant idea that beneath the vast complexity of human thought, there might be one general force tying it all together. They call it the G factor, short for general intelligence. It's the theory that if someone excels in one area, say, math, they're also more likely to perform well in others, like vocabulary, problem solving, or reading comprehension. This isn't just a casual observation. It's a pattern that's shown up repeatedly in research. People who score high in one domain tend to score high across the board. It's as if a shared cognitive engine G powers multiple mental abilities at once. The implications are huge. If we can identify and understand this common factor, we could gain profound insight into how intelligence functions, why some people learn faster or solve problems more efficiently, and what might help boost or support this general ability. A fair amount of evidence backs this idea. Across large populations, scores on different cognitive tests are often correlated. That correlation suggests there's something unifying, a mental thread running through our capacity for logic, language, memory, and comprehension. Of course, the G factor isn't the whole story. Different people have different cognitive strengths, and intelligence is influenced by countless variables from genetics to education to environment. Still, the quest for G remains central to modern psychology, a powerful reminder that intelligence may not be a scattered set of skills, but a tightly woven network built on a deeper, shared foundation. So how much of our intelligence can actually be explained by this elusive G factor? Surprisingly, quite a lot. Most large-scale studies suggest that G accounts for about 40 to 50% of the differences in performance between individuals on IQ tests. That's not everything, but it's a significant chunk of the cognitive puzzle. In other words, if you're trying to understand why some people excel on tests of logic, language, memory, or reasoning, nearly half the answer may come down to a shared general capacity at the core of their minds. But it gets more interesting. The G factor doesn't just exist in test results, it appears to have real-world consequences. Research shows that G can predict academic performance fairly well, especially in early schooling, where tasks rely heavily on general learning ability. It also correlates, to some extent, with career outcomes, especially in fields that require complex decision-making, problem-solving, or abstract thinking. But G doesn't act in isolation. It's shaped by both nature and nurture, and many studies suggest that it's highly heritable. Estimates vary, but genetics may account for 50% to 80% of the variability in G across individuals, especially as they age. That doesn't mean intelligence is fixed or predetermined, but it does mean that some people may start with more cognitive horsepower, even if how they use it is influenced by environment, education, and opportunity. Interestingly, G also shows a moderate correlation with brain volume. People with larger overall brain size tend to score slightly higher on intelligence tests. But this link is not especially strong, suggesting that how your brain is organized may matter more than its size. So while the G factor is not the full picture of human intelligence, it remains one of the most consistent and predictive threads. Psychologists have uncovered a core cognitive currency that influences learning, success, and perhaps even potential. If general intelligence, the mysterious G factor, correlates somewhat with brain size, you might think the story is simple: bigger brain, smarter person, but the reality is far more complex. Yes, there is a moderate link between total brain volume and G, and even a modest correlation between height and intelligence. Taller people tend to have larger brains simply because they have larger bodies overall, and with more brain tissue, on average, may come slightly better performance on some cognitive tasks. But here's the key: brain size only explains a small part of the picture. The majority of the variation in general intelligence has nothing to do with how large your brain is or how tall you are. In fact, brain efficiency, connectivity, and specialization seem to matter more than volume. A smaller brain with finely tuned networks, high-quality white matter, and effective communication between regions can easily outperform a larger one with poor structure or slow processing. Height may statistically correlate with G across large groups, but it doesn't determine the depth, creativity, or adaptability of your mind. And crucially, correlations do not imply causation. Height and intelligence may both be influenced by shared genetic or environmental factors such as nutrition, early development, or socioeconomic status. So while it's tempting to equate size with smarts, The truth is that intelligence is less about how much brain you have and more about how your brain works. Ultimately, intelligence isn't a matter of centimeters or grams, but of complex architecture, adaptability, and experience. Once the concept of the G factor took hold in psychology, researchers began to realize that this general intelligence wasn't a single, monolithic ability. Instead, it could be meaningfully divided into two distinct but related types: fluid intelligence and crystallized intelligence. Think of them as the difference between quick thinking and earned wisdom. Fluid intelligence is your raw mental horsepower. It's the ability to solve new problems, identify patterns, think abstractly, and adapt on the fly even when you have no prior knowledge or experience to rely on. It's what you use when you're figuring out a puzzle, troubleshooting a tech issue, or analyzing something unfamiliar. This type of intelligence peaks in your 20s, when your brain is at its most flexible and agile. Crystallized intelligence, on the other hand, is the accumulated knowledge and understanding you've built up over time. It includes vocabulary, general knowledge, life experience, and the strategies you've learned for solving problems efficiently. In other words, it's what you know and how you've learned to apply it. Unlike fluid intelligence, crystallized intelligence tends to remain stable or even improve with age as long as you keep your brain active and engaged. Reading, conversation, creative thinking, and continued learning all strengthen this mental resource. So while you might be a faster thinker in your 20s, you may well be a wiser thinker in your 40s, 50s, and beyond. Together, fluid and crystallized intelligence form the two pillars of your cognitive abilities, one giving you speed, the other giving you depth, and both are essential for navigating the challenges of a complex world. Despite the strong evidence supporting the existence of the G factor, whether in its fluid or crystallized form, not all psychologists are comfortable with the idea that intelligence boils down to a single, core ability. After all, human abilities are incredibly diverse. Is it really fair to define intelligence only by what shows up on an IQ test? One of the most influential critiques comes from psychologist Howard Gardner, who proposed the now famous theory of multiple intelligences. According to Gardner, intelligence isn't one unified thing, it's a spectrum of different cognitive strengths, many of which aren't measured in traditional testing. His theory identifies at least 8 distinct types of intelligence, including linguistic word smart, logical mathematical number smart, musical sound smart, bodily kinesthetic body smart, spatial visual smart, interpersonal people smart, intrapersonal self smart, naturalistic nature smart. This model embraces abilities that IQ tests tend to overlook, like social intelligence, emotional awareness, artistic skill, and physical grace. It explains why someone might struggle in academic settings yet excel as a leader, artist, athlete, or empath. Critics of Gardner's theory argue that some of these intelligences might be better described as talents or personality traits, and the G factor still remains a powerful predictor of performance in many structured environments, like school or certain jobs. But Gardner's work opened the door to a broader, more human view of intelligence, one that values diversity in thinking, feeling, and relating, and one that asks, what does it really mean to be smart? In contrast to the traditional view of intelligence as a single, unified trait, Howard Gardner proposed something radically different. There is no one kind of intelligence. Instead, he argued, the human mind is equipped with multiple intelligences, each representing a unique way of perceiving, processing, and expressing information. In his theory, Gardner identified several distinct types, including musical intelligence, the ability to perceive rhythm, pitch, and melody, think in sounds, and create or appreciate music; visuospatial intelligence, the capacity to visualize the world in 3D, manipulate objects mentally, and understand spatial relationships often seen in artists, architects, or pilots; verbal linguistic intelligence, skill in using language, both spoken and written, often strong in writers, speakers, and storytellers; logical mathematical intelligence, the ability to reason, recognize patterns, and solve abstract problems, a hallmark of scientists, engineers, and mathematicians; bodily kinesthetic intelligence, control of body movements and fine motor skills, often evident in dancers, athletes, and surgeons; interpersonal intelligence, sensitivity to others' emotions, motivations, and intentions; Essential for leaders, teachers, and counselors, intrapersonal intelligence, deep self-awareness, the ability to reflect, and a strong understanding of one's own emotions and drives, naturalistic intelligence, the ability to recognize patterns in nature and classify plants, animals, or ecological systems. Common in biologists, gardeners, or environmentalists, Gardner's theory reframes intelligence not as a fixed score, but as a dynamic and multifaceted set of capacities. It acknowledges that people excel in different areas and that intelligence shows up in ways beyond academic tests or logical puzzles. His work invites a broader question. What if being smart doesn't look the same in every person? And what if valuing only one kind of intelligence blinds us to the richness of human potential? Gardner's theory of multiple intelligences caught on quickly, especially in educational circles. It offered a refreshing alternative to the narrow view of intelligence as something measured solely by standardized tests. For teachers, parents, and students alike, it felt empowering, a recognition that people think and learn in vastly different ways. But despite the widespread appeal and intuitive charm of the idea, scientific support for Gardner's model remains limited at best. While the theory is rich in philosophical value and practical inspiration, empirical studies have struggled to validate the existence of these distinct, independent intelligences. Unlike the G-factor, which has decades of data behind it, Gardner's framework has not been consistently backed by cognitive or neurological research. Critics argue that many of the so-called intelligences are more accurately described as talents, skills, or even personality traits, rather than standalone cognitive systems with their own mechanisms in the brain. Still, Gardner's theory shifted the conversation from measuring intelligence to appreciating human diversity in how we think, feel, and learn. So while the science may not fully support the multiple intelligences model, its cultural and educational impact is undeniable. Fortunately for science, and perhaps controversially for ethics, Albert Einstein's brain was preserved after his death in 1955, allowing researchers to study it in hopes of uncovering the biological roots of his extraordinary intellect. Over the years, different studies have analyzed various regions of his brain, comparing them with those of average individuals. One particularly intriguing finding involved the ratio of neurons to glial cells. Neurons are typically considered the brain's stars, the cells responsible for processing and transmitting information. Glial cells, on the other hand, are the vital support crew. They maintain the environment around neurons, deliver nutrients, remove waste, and assist in communication. In at least 4 separate regions of Einstein's brain, and when compared with a control group that included war veterans, researchers found that he had a lower ratio of neurons to glial cells. This means that, relative to most people, Einstein had more support cells per neuron. Some scientists speculate this could suggest that his neurons were better nourished, more efficiently maintained, or able to function with greater stamina, potentially contributing to his remarkable cognitive endurance and abstract reasoning abilities. However, these findings are far from conclusive. The sample size is small, the comparisons limited, and it's unclear whether this ratio was cause, effect, or coincidence. After all, genius likely doesn't reside in a single ratio but in a complex interplay of biology, environment, and experience. Still, the study of Einstein's brain continues to capture imaginations, not because it offers easy answers, but because it reminds us of how little we truly understand about the nature of intelligence. While the discovery of a different neuron to glial cell ratio in Einstein's brain sparked interest, the evidence was far from definitive. Out of the 4 brain sections analyzed, only one showed a statistically significant difference in this ratio. That means the supposed uniqueness of Einstein's brain could very well be a fluke of measurement, not a consistent pattern. Moreover, the study's methodology raises questions. The researchers were not blinded. They knew which brain slices belonged to Einstein and which belonged to the war veterans used for comparison. This opens the door to confirmation bias. Even if unconscious, when you're looking at the brain of a genius, you might be more inclined to find something extraordinary, whether it's truly there or not, adding to the speculation. One paper even used the Lauer neuron to glia ratio in Einstein's left parietal lobe as a potential explanation for his reported dyslexia, but that connection is highly tenuous. There's no solid evidence Einstein was clinically dyslexic, and linking a specific cognitive trait to a single brain ratio, especially from post-mortem slices, is overly simplistic in the end, while the story of Einstein's brain makes for fascinating headlines, it also serves as a reminder of how easy it is to read too much into tiny anatomical differences, especially when studying a mind as mythologized as his. Further research into Einstein's brain turned to a region critical for advanced thinking, the prefrontal cortex, the seat of planning, reasoning, and abstract thought. Surprisingly, analysis of one section from this area revealed that Einstein's cortex was thinner than that of age-matched controls. At first glance, this might seem counterintuitive. In many neuroscientific studies, greater cortical thickness is associated with cognitive health. Especially in younger adults, thinning of the cortex is often linked to aging, stress, or neurodegenerative diseases, such as Alzheimer's, but in Einstein's case, the thinner cortex wasn't necessarily a sign of weakness because the neurons in that region were more densely packed. This suggests that his brain may have been optimized in a different way, rather than spreading out across a thicker layer. His neurons were concentrated and tightly interconnected, possibly allowing for faster processing or more efficient communication between cells. Still, the interpretation of these findings remains speculative. Does a dense network mean better thinking? Or was this simply a variation within the wide range of human neuroanatomy? As with other anatomical observations of Einstein's brain, the evidence is intriguing, but the sample is limited, the context incomplete, and the causal links to genius remain elusive. Rather than offering answers, these findings invite a deeper question: what really makes a brain brilliant? Its structure, its wiring, or the life it lives? It's tempting to believe that Einstein's densely packed neurons in the prefrontal cortex were a key to his brilliance. After all, if neurons are closer together, they might communicate more rapidly and efficiently, allowing for quicker thought, deeper connections, or more complex reasoning. But here's the problem: dense doesn't always mean better. In fact, studies have shown that individuals with schizophrenia disorder, often marked by disorganized thinking and cognitive disruption, can also have more densely packed neurons in the prefrontal cortex. So while it's possible that increased neuron density offered Einstein some cognitive advantage, it's equally possible that such structural features aren't inherently beneficial. Context matters: how the neurons are wired, how they interact with glial support cells, how efficiently they fire, and how life experience shapes those networks all influence function far more than just packing density alone. This comparison underscores a crucial point in brain science. Structure doesn't always predict performance, and a single anatomical trait rarely explains something as rich and complex as intelligence. What made Einstein extraordinary was likely not one physical characteristic, but a synergy of biology, environment, personality, and relentless curiosity. If overall brain size doesn't fully explain intelligence, perhaps the secret lies in the composition and structure of specific brain regions, particularly those involved in problem solving, memory, language, and abstract reasoning. That's exactly what many neuroscientists are beginning to suspect. Instead of focusing on total brain volume, researchers are exploring whether certain areas of the brain, like the prefrontal cortex, parietal lobes, and hippocampus, are more closely tied to performance on IQ tests and other measures of cognitive ability, and the evidence is mounting. Multiple studies have found that individuals who score higher on IQ tests often show subtle but consistent differences in brain structure, greater gray matter volume in certain regions, increased connectivity between networks, and even thicker or more complex folds called GYRI and sulci in areas related to attention, working memory, and reasoning. In other words, it's not just how big your brain is, but how it's organized, how efficiently it communicates, and which parts are emphasized or refined. This perspective moves the conversation beyond simple measurements and into the nuanced architecture of the mind, where intelligence may be less about volume and more about functional design and neural cooperation. When it comes to uncovering the neural roots of intelligence, most studies fall into two broad categories, each examining a different part of the brain's architecture. The first group of studies focuses on gray matter, the brain tissue that contains neurons and is largely responsible for processing information. Managing memory and executing complex thinking, more grey matter in certain regions is often linked to greater cognitive abilities and is thought to reflect a higher number of active neurons available for problem solving and mental effort. The second group turns its attention to white matter, the network of connections that allows different brain regions to communicate with one another. White matter is made up of myelinated axons, which act like highways carrying electrical signals between neurons at high speeds. Here, researchers are looking at how efficiently information travels across the brain. Strong, well-organized white matter networks can allow for faster processing, better coordination, and more integrated thinking. Together, grey matter and white matter paint a richer picture. It's not just about how many neurons you have, but also how well they work together. A brain with lots of neurons but poor communication is like a city full of brilliant people with no way to contact each other. So while intelligence can't be boiled down to a single structure or system, these two types of brain tissue offer important clues to how our mental capacities are wired and why they vary from person to person among all the regions of the brain. The frontal lobes, particularly the prefrontal cortex, appear to play a central role in what we commonly think of as intelligence. Research has consistently shown that grey matter volume in these areas correlates with IQ scores, especially on tasks that tap into the G factor, the general cognitive ability believed to underlie performance across many domains. For example, when people engage in spatial reasoning or verbal problem solving, two tasks often featured in intelligence tests, certain areas in the front of the brain light up. These regions are responsible for planning, decision-making, abstract thought, and working memory, all core components of what IQ tests aim to measure. What's especially interesting is this: the more grey matter present in these frontal regions, the better the performance tends to be. It's as if having more neurons in this executive hub gives the brain greater mental bandwidth, allowing it to juggle information more effectively, filter distractions, and adapt quickly to new problems. Of course, intelligence is complex and multidimensional, but the frontal lobes are often considered the command center, coordinating thoughts, goals, and actions. Their structure and density seem to offer a tangible neural foundation for at least some aspects of intellectual ability. One of the clearest ways to understand the role of the frontal cortex in intelligence is to look at what happens when it's damaged. Patients with injuries or degeneration of grey matter in this region, whether due to trauma, stroke, or neurodegenerative diseases like Alzheimer's, often experience a noticeable decline in cognitive function. Their performance on intelligence tests typically drops, especially in areas related to problem solving, reasoning, and decision making, but the effects go beyond test scores in daily life. These individuals often struggle with judgment, impulse control, and goal-directed behavior. They may make decisions that are clearly irrational, inappropriate, or even dangerous despite retaining other abilities like memory or language. This real-world evidence underscores how central the prefrontal cortex is to what we call intelligent behavior. It's not just about having knowledge, it's about using it wisely, adapting to changing situations, and thinking ahead. Damage to this region reveals that intelligence isn't just stored in facts or formulas, it's embedded in the networks that help us weigh options, anticipate consequences, and act with intention. A function that, when impaired, makes even the most basic daily tasks feel overwhelming or confusing. In short, when the frontal lobes go offline, so does much of our higher-order thinking. Intelligence, at least in part, depends not just on what we know, but on how well our brain can use what we know. When it comes to intelligence, maybe size does matter, at least when we're talking about the frontal lobes. The volume of grey matter in these regions does seem to correlate with performance on tasks requiring abstract reasoning, memory, and decision-making, but the story doesn't end or begin with size alone. For one thing, the frontal cortex doesn't operate in isolation. No part of the brain does. Intelligence isn't housed in a single lobe or cluster of cells. It emerges from communication, from the constant exchange of signals between billions of neurons across multiple brain regions, and that's where things start to get more complicated and more interesting, because the real work of the brain doesn't happen just within neurons, but between them. It's in the connections, the pathways that allow different parts of the brain to talk to each other, to integrate new information with stored knowledge, to weigh risks, solve puzzles, And imagine the future. This is the realm of white matter, the brain's vast communication infrastructure. While grey matter might represent the raw computational power of the brain, white matter is what makes the system coherent. It links the frontal lobes to other key areas involved in perception, emotion, memory, and language, enabling the kind of fluid, integrated thinking that underlies intelligence. So yes, size may play a role, especially in the frontal cortex, but connectivity, how well information moves, how efficiently neurons synchronize their activity, may be just as important, maybe even more so. While grey matter is often associated with the raw processing power of the brain, white matter represents the network that connects it all together, the highways along which thoughts, decisions, and perceptions travel. These bundles of myelinated axons link neurons across different brain regions, enabling complex coordination between areas responsible for memory, attention, emotion, and reasoning. In essence, white matter is what allows the brain to function as a unified system, rather than isolated parts working in silence. The more white matter you have and the more intact and efficient those connections are, the better your brain can communicate with itself. Signals are sent faster, more reliably, and with greater clarity. That's why scientists studying intelligence are increasingly focused on white matter integrity. They're not just asking how big is your brain, but how fast can your brain talk to itself? The theory is simple but powerful. Faster communication leads to faster thinking, and faster thinking, in turn, often translates to higher intelligence. This is sometimes referred to as exploring the neural correlates of mental speed. A person with richer white matter networks may be able to process incoming information more quickly, retrieve knowledge more efficiently, and adapt to new situations with greater ease. So while grey matter may provide the horsepower, it's white matter that determines how smoothly and how fast the engine runs. Research has consistently shown that white matter volume and integrity are linked to how well a person performs on intelligence tests. One of the clearest examples of this connection lies in the corpus callosum, the brain's largest white matter structure. The corpus callosum acts as the bridge between the two hemispheres, allowing information to flow seamlessly between the left and right sides of the brain. This crosstalk is essential for tasks that require integration of language, logic, emotion, and spatial reasoning, the kind of multi-dimensional processing that shows up on IQ tests and other cognitive assessments. Studies have found that individuals with a larger or more structurally sound corpus callosum tend to perform better on a variety of cognitive tasks, especially those that demand rapid problem solving, flexible thinking, or coordination between analytical and creative skills. However, like most findings in neuroscience, the results aren't universally consistent. Not all studies show statistically significant effects for every measure of callosal volume. The brain is complex, and intelligence is influenced by many overlapping factors, including grey matter, white matter integrity, brain network efficiency, genetics, environment, and experience. Still, the corpus callosum remains a key piece of the puzzle. Its size and health appear to play a role in how efficiently the brain can integrate information, and that efficiency may be part of what we call intelligence. While white matter plays a crucial role in the speed and efficiency of brain communication, some neuroscientists argue that grey matter may be even more important when it comes to understanding the neural foundations of intelligence. Grey matter is where the thinking happens. It houses the cell bodies of neurons and is responsible for processing, decision-making, memory, attention, and sensory perception. It's the command center of the brain, while white matter acts more like the communication network that links those command centers together, because grey matter density and volume are often correlated with higher scores on tasks involving abstract reasoning, verbal fluency, and working memory. Many researchers believe it may be a more direct marker of raw cognitive capacity. In other words, more grey matter may mean more processing power. The mixed evidence around white matter's role, with some studies showing strong correlations and others showing weaker or inconsistent results, has led some scientists to prioritize grey matter in the search for the neural basis of intelligence. However, this is not a case of either or. The most likely truth is that intelligence arises from a dynamic interplay between grey and white matter. Grey matter provides the cognitive horsepower. White matter makes sure that power can be accessed and coordinated across the brain's regions. So while grey matter might be the star of the show, white matter is the director backstage, making sure everything flows smoothly. Neither works Well, without the other, and both help shape the incredible variability of human intelligence. Brazilian neuroscientist Susana Herculano Hausel shook the foundations of traditional neuroscience by developing a new method for accurately counting brain cells, a technique that sidesteps the assumptions and estimations of earlier approaches. And what she found has called into question one of our most cherished ideas, that the human brain is uniquely special. Her research suggests that our brains may not be so extraordinary after all. In fact, when she compared the number of neurons in the human brain to those in other species, particularly primates, the results were surprising. We're not outliers in the way we thought. This calls into question the continued use of the encephalization quotient EQ, the measure that compares an animal's actual brain size to the expected size for its body mass. The EQ has long been used as a way to argue that humans are biologically exceptional, but as Herculano Hausel points out, EQ may be more a product of our desire to feel special than a scientifically sound metric. She argues that the persistence of EQ in neuroscience might have less to do with evidence and more to do with confirmation bias, our tendency to focus on data that reinforces what we already believe. In this case, EQ offers a comforting narrative that our species sits proudly above the rest, evolutionarily privileged and intellectually superior. But if we strip away that bias and look purely at the data from brain cell counts, a different picture emerges, one where human intelligence isn't the result of a miraculous leap, but rather the predictable outcome of scaling up primate brains while maintaining a high neuron density, especially in the cerebral cortex. According to Herculano Hausel, what makes our brains powerful isn't their size, it's the sheer number of cortical neurons packed inside, and even that is a matter of biology and energy availability, not divine exception. It may not be that humans evolved especially large brains compared to our primate cousins, but rather that other primates evolved larger bodies while their brains stayed the same size or even shrank. In other words, the human brain might not be an outlier for its exceptional size, but for its efficiency, the result of evolution preserving brain size while keeping the body relatively small. This flips the usual narrative. Instead of asking why did humans evolve such big brains, we might ask why did other primates evolve such big bodies without a matching increase in brain power? From this perspective, it's not that our brains are unusually expensive, it's that other species evolved cheaper bodies. If brain size remained relatively stable while body size grew, then the brain-to-body ratio, a key metric in intelligence comparisons, would appear smaller in our cousins, not because they are less intelligent, but because their bodies grew faster than their brains could keep up. This reframing suggests that evolution is not always about adding more, but sometimes about keeping the right balance, and it reminds us that intelligence might not stem from having the biggest or most expensive brain, but from maintaining the optimal brain-body trade-off that evolution could afford. Humans do not have the biggest brains in the animal kingdom, not by a long shot. Whales and elephants far surpass us in brain volume, but here's where things get interesting. Size alone doesn't tell the whole story. Brazilian neuroscientist Susana Herculano Hausel developed a method to accurately count neurons, and her research overturned a long-standing assumption. She discovered that bigger brains don't always mean more neurons. In fact, when comparing brains of equal size, primate brains contain far more neurons than those of rodents or other mammals, so a primate brain and a rodent brain of the same volume aren't even in the same league when it comes to neural density. This means that a smaller brain with more neurons may be far more cognitively powerful than a massive brain with fewer. The human brain, while not the biggest, is incredibly neuron-rich, particularly in the cerebral cortex, the region most associated with higher-order thinking. That's what makes our brain so expensive in evolutionary terms. Not its size, but its dense, energy-hungry network of neurons. In this light, it's not about having the biggest brain, but about having the most efficient and densely packed, expensive real estate in the right regions. Susana Herculano Hausel developed a groundbreaking model to estimate how many neurons and support cells like glia should exist in a primate brain of a given size. Her model offers a kind of neural blueprint for what a typical primate brain should look like if evolution simply scaled up logically. According to her predictions, a brain the size of a human's, if it followed the usual primate trend, should have around 93 billion neurons and approximately 112 billion glial cells, but when scientists actually counted the cells in the average human brain, the numbers came in lower than expected, about 86 billion neurons and 85 billion glial cells. What does that mean? It suggests that the human brain, rather than being an outlier or exceptional in terms of neuron count, is actually right on track for what you'd expect from a primate brain of our size. In other words, we're not uniquely special by structure alone. Our brain isn't overbuilt, it's just efficiently constructed. Balancing function and metabolic cost, this challenges the myth that our intelligence stems from some magical leap in neuron numbers. Instead, it's how those neurons are organized, connected, and maintained that gives rise to our cognitive abilities, not just how many we have. Our primate cousins, the great apes, actually have smaller brains than their body size might suggest, and the reason may come down to something surprisingly simple: energy. Neurons are incredibly expensive to run, they consume vast amounts of energy. Even when you're at rest, for animals like gorillas and chimpanzees, there's a biological trade-off. They can't eat enough high-energy food to support larger brains. Their digestive systems, diets, and daily routines just don't allow them to generate the extra fuel that additional neurons would require. So evolution placed a limit not based on potential, but on practicality. This energy-based limit may also help explain why human babies are born with relatively small brains, instead of trying to develop a fully mature, energy-hungry brain in the womb when the mother is already near the edge of her metabolic limit. Nature takes a different approach: birth the baby early and let the brain continue growing outside the womb, where more energy can be sourced over time. In this view, calories are the true currency of brain power. And the size of a brain isn't just a matter of genetics or evolution, but also fuel supply and energy efficiency. One of the most compelling theories about why humans are able to support such large, energy-hungry brains is surprisingly simple. We learned how to cook. Cooking fundamentally transformed human evolution. By heating food, we digest it, making nutrients more accessible and reducing the energy needed for digestion. This shift meant our bodies could extract more calories faster from the same amount of food. In turn, that extra energy could be diverted to fueling the brain, one of the most metabolically expensive organs in the body. But the impact of cooking goes beyond biology. It gave us more free time. Time we didn't need to spend chewing raw roots or hunting constantly for calories. That extra time may have been the catalyst for culture, communication, collaboration, and ultimately cognition. In this light, our intelligence isn't just a product of brain structure, it's a byproduct of a simple fire. Cooking may be the ultimate brain hack, the tool that allowed evolution to shift energy toward thinking, imagining, and creating the world we live in today. Herculano Housel's work delivers a final blow to the long-standing belief that brain size, or even the encephalization quotient, is what sets humans apart. Her findings show that these numbers, while once convincing, don't tell the full story. What truly makes us unique isn't having the biggest brain, it's having the most neurons our bodies can afford to fuel and figuring out how to get enough energy to sustain them. That breakthrough came with a simple but revolutionary act: cooking. By learning to cook our food, humans unlocked more calories with less effort. This allowed our species to nourish more brain cells, not just to survive, but to think, imagine, and create. So what makes us special? Not oversized brains or abstract quotients, but our ability to turn an ordinary primate brain into an extraordinary thinking machine powered by fire, food, and the time to wonder. However, Herculano Housel cautions against using her model to estimate the number of neurons in individual members of a species. While her method works well for broad comparisons between species, it falls short at the individual level. Her research has revealed that neuron density can vary significantly within a single species, and this variation doesn't consistently align with brain size. In other words, having a larger brain doesn't guarantee more neurons, not even among individuals of the same kind. Some people may have denser, more efficient networks in smaller brains, while others with larger brains may house fewer neurons. This disconnect between size and cellular content further challenges the idea that brain volume is a reliable indicator of intelligence. It's yet another reminder that when it comes to the brain, bigger isn't always better, and biology rarely follows a simple rule. If you'd like to dive deeper into the science behind brain structure, intelligence, and cognitive evolution, these sources offer rich insights. Eric Chudler's Brain Facts and Figures provides a clear and accessible overview of brain anatomy, neuron counts, and basic neuroscience concepts perfect for building foundational knowledge. Susanna Herculano-Hausels, The Human Brain in Numbers offers a transformative view on how we count neurons and what those numbers really tell us about intelligence and human uniqueness. Terence Hines explores the myths surrounding genius in Neuromythology of Einstein's brain, challenging long-standing assumptions about what made Einstein's brain different or not. Robert Plumman and Frank Spinath present critical findings on the genetic influences on intelligence in their paper Intelligence, shedding light on nature vs. nurture debates and how heritable cognitive traits may be. Arthur W. Toga, Margaret J. Wright, and Paul M. Thompson take a deep dive into the genetics of white matter development, showing how the brain's connective infrastructure impacts our thinking speed and mental performance. These readings provide a fascinating window into the neuroscience of intelligence and the complex biology behind what makes us think, remember, and create.